Guess what? We're back on electric turbo stuff. Well, let's not waste time. This has been a long time coming. Let's get right to it. We are going to test a different motor ESC combination on the cheaper, more affordable, easier to assemble, but still similar performance, P2 based electric turbo or electric supercharger if you want to be technical about it, but let's not be technical because more people search for electric turbo than they search for electric supercharger. But you don't care. What you care about is what's over to my right. Meet the victim. This is a Hobbywing. It's actually quite nicely made. So how does this thing compare? It comes in a nice box, by the way, and I'm not going to unbox it. Who cares, right? So it's actually really, really robust. This is not plastic. This is aluminum. I would say it's in the same league as the APD ESCs, but it's physically larger. This one is only rated to 12S, where the APDs, I believe, could go all the way up to, what was it, 15, 16S, somewhere in there. But what's interesting is even though this one's only rated at 12S, which technically gives you a max voltage rating of 50.4 volts, and by the way, that's what the Castle motor is rated for, this one has 63 volt capacitors inside. I already kind of, looked through the cooling vents here and figured that out. And what's interesting to note, the big bad MGM ESC that's running the LMT motor in the Sledgehammer unit, which is an awesome unit. I mean, those things are fantastic, but they're kind of costly. That one also runs 63 volt capacitors. So far we're off to a good start. I can tell you this, I took this thing out of the box, hooked it up, did some relatively low power tests. We got up to about 12,000 motor RPM just to make sure this thing works. But we are going to torture this thing. We are going to see if its ratings are for real. Can it really handle 300 continuous amps? It's supposed to have a 2,000 amp peak rating. Like I said, it's pretty robust. The only weird thing about this is this sensor cable is a proprietary connector. And in the ad, it said that the adapter cable for the more standard connector is included, but it's not. But to their credit, I reached out to the company and they said, yeah, they changed their policy on that and they're not really including them anymore. But they are sending me a sensor cable. Whether it gets here in time, it would have to get here tomorrow. I don't know if it will because I'm doing this tomorrow night. This is the day before. This is like, your last meal, my friend, unless you are good for what you say you're good for. The model of this one is their big boy. This is the biggest one they make as far as I know. This is the Easy Run Max 4. It's about $450 US at the time of this video. I paid full price for it, like I do most of these things. You do have to turn it on with this button. You program it with a little LCD programmer. I'm looking for where that thing is right now, and it is hiding from me at the moment. Why are you hiding? Well, that took way too long, but this is the programmer. This is like the luxury model. This thing has a little screen. It tells you what the parameters are. You can set it this way. By the way, what's funky about this particular ESC and how they do it is the programmer actually plugs into the fan port. Weird, I know, right? But it works. As I mentioned, this is a luxury model. There is a cheaper version that's like 10 bucks or less. This is like 25. It's not expensive. It's like 25 bucks. The cheaper version is basically just 8-digit LED display, basically the same thing. But overall, this ESC is, in fact, considerably cheaper than the other ones we've been working with. It's cheaper than the Vesk, which sadly didn't perform as it should have. Hit a fault. Yeah, the current starts to ripple pretty severely, and honestly, I don't know why. It's cheaper than both APDs by a good bit, anywhere from less than half to less than a third, so that's not unsubstantial, and it's about a quarter the price of the MGM ESC. Having said all that, the quality is actually quite decent, but what you give up is you give up some programming, you give up some data logging, but let's be honest, we're spinning an impeller. We're not driving a car. We're not flying a plane. All we need is something that lives up to its ratings and can take some pretty hefty power loads. That's all we're looking for. Let's keep it simple. So towards that end, this does have one parameter which I like, and that is you can set up how much punch it has. So that is, how quickly it accelerates. I have this currently set to a punch level of 1, which is the softest. And it starts that thing pretty aggressively. But again, you know, no sensor cable, so it's not like brutally bad, but I can only imagine what the max level, which is like 5 or something. I don't know what it is, but maybe 9. I think it varies depending on the model of the ESC. Anyway, so this is our victim. We're going to send it into the Thunderdome, which is over there because it's freaking freezing outside. And I'm not doing this in my garage, so instead I've chosen to make yet another incredibly poor decision and do this indoors, in my house, in my sunroom, under a chandelier. I make poor choices. Anyway, so that's that. So far, very impressed. It was very easy. Took it out of the box and it just freaking worked, unlike the Vesk, which I screwed around with for like literally weeks and couldn't get it to work right. This thing just worked out of the box, like the MGM, like the APDs, like the Flyer ESCs, but the Flyers were kind of liars. Their ratings, hey, that rhymes. Their ratings were like nowhere close to reality. This thing, though, I don't doubt. This thing, like I said, it's very, very nicely made. It's of the same quality case-wise as the APDs were. It's just a nice, I mean, it's a pretty beefy unit. This thing's not exactly lightweight. So, before we get over to the test cell of doom, I want to share a few important measurements. Let's do that. To install these things in an actual vehicle, like a real car, not on some like complete, total, like nonsensical bench test, which doesn't do anything really at the end of the day, because, you know, you can get anything running. We need to extend the battery cables or the motor cables. And I've had more luck extending actually the battery cables than I have with the motor cables. But of course, the MGM just works with everything but then again, it's also running censored. And I think that makes such a big difference. You know, a lot of RC guys will say, oh, just make the motor cables as long as you want. Well, that's actually not true unless you're running a sensor, because what ends up happening is the motor or the ESC can never sync up to the motor if the cables are too long. I've found that like several different ways through multiple brands of ESCs. So when we were running the APD ESC, which was the first time we drag tested the thing, and you know, the thing moved out, went 127 miles an hour in a quarter mile. That ain't bad for a, you know, a mid-80s 3,500 pound sedan. We had long power cables, and I used these capacitors. These I have re-sleeved because they were well involved in a fire, but they still test fine. You know, I printed out their model number and all that here, but these are what we're going to use. But I did also want to make a point that you don't need to throw down for, you know, the Panasonic caps or whatever. I mean, these are big units because I'm not using these in RC vehicles. I've got room for these things. These are 3 Nippon Chemicon, so they're a really good brand, caps that I pulled out of Computer Power Supply, I believe. And I wanted to show you that these were like really expensive. These were like, I don't know, $40 each or something. And they are actually made in Europe. And I wanted to compare these. So these have a 100 volt rating and they're 20,000 microfarads each. These have a 63 volt rating. So not, you know, can't handle the same voltage level as these can, but they're 63 volts, but they're 22,000 microfarads each. Or microfarads, whatever. Anyway, so what this thing is here is this is an ESR meter, effectively. And it's actually a battery internal resistance tester. So what I wanted to show you, actually, I wanted to show you something else that was kind of cool. I've got a little wrench here. So check this out. So like if you just, this will really illustrate why it's important to properly tighten your connections. So if I just take these 2 little nuts here and just kind of hand tighten them, I got to make sure I get the polarity absolutely correct and that you can actually see the screen. Let's put a Wago connector under here. That'll probably work. Yeah, okay. All right, so these are what's called Kelvin clips. They have wires going, 1 wire going to each side of the actual clippy clip itself. And it does that so it can measure these insanely low resistances. And so basically what this does is it sends an AC frequency and then measures the resistance through the capacitor or the battery. It works on both, actually. All right, so that's finger tight. We are getting 8.9 milliohms. Finger tight. That's a little high. I mean, it's pretty low for capacitors. These are specifically low ESR capacitors. But let's tighten those little nuts. Little wieners and tiny nuts. Name that movie. It's actually kind of more of a kid's movie. But it's pretty funny, though, nonetheless. So that's just kind of snug. You don't want to go nuts with the nuts. That's a lot of nuts. But now look, we're down to almost half, 4.2, 4.3 milliohms. That is a true low ESR cap pack. That's what you want, somewhere down there or less. So how do my recycled computer power supply ones compare? Well, let's find out. These actually makes more sense if I turn them around this way so I can actually clip the Kelvin clips on. And so both sides make contact. So look at that. It's pretty much the same. The voltage is pretty low too. Look, 0.346. It's not even a volt. So what happens if we charge these up? Do they change ESR? Does the ESR value change? I phrased that very poorly. Let's find out. Let's pump, well, this is set to 12.5 volts. So we're going to pump 12.5 volts through it. And the voltage is already out. This may spark just a little bit. Nope. And they're charged. It's just that quick. And that was set at 1 amp, by the way. That was current limited. So now you're going to see somewhere, well, significantly above what it was before. And the ESR should still stay the same. You never want to do this with a regular resistance meter. You'll blow it up. But again, this is specifically designed to measure batteries. And of course, it can also do capacitors. We want to see if it changes. Look, it's 12 volts. But the ESR is exactly the same. Didn't change. So while we're at it, and we're playing fun and games, and you're getting information that you'll see pretty much nowhere else, we are going to use, this is a 4S pack, 9,000 milliamp hours, obviously, you know, from Z batteries. This, actually, we can use this to figure out what the projected voltage drop is going to be. These are a little harder because you kind of have to expand the clips. But we are at 5.7 milliohms. That's pretty, it's a little tricky. But I'd say 5.7 is a reasonable number. You know, let's look at another pack. And I am going to top these off before we go into the Thunderdome of Doom over there and try to blow the thing up. 5.7, 5.6. They all pretty much measure exactly the same. So I am going to run 3 of these packs, giving us 12S. But these are also going to be in parallel with my 6,000 milliamp packs. This is what I actually started with back in the day, because why not? This will give us a little extra current capacity. Not the greatest idea. Puts a little bit more load on one set of cells over the others. But, you know, hey, we roll with what we got. This stuff is expensive. So, and these are in the mid to low 7 milliohm range. All right, so let's say our average is 6 milliohms. Let me just jump in here because I screwed up the math. My parallel resistance calculation was wrong. I did it in my head and wasn't really paying attention. The voltage drop is going to be about 2.88 volts within the batteries. There's about a 1 volt drop within the cables. Then add in another couple volts drop. So 3, 4, 5, 6. We should have roughly 44 battery volts under load if we hit 300 amps. It's going to be interesting to see how the theory translates to reality. Speaking of reality, let's go see if it'll blow up and burn my house down. All right, let me walk you through this whole setup. Everything is currently powered up. This is a photo-optical tachometer that I bought. It's like under 20 bucks, but I've taken the sensing part out of it, stuck it to a PC board to maintain the geometry, stuck that in a PVC tube, put that in heat shrink, and that is right here, and that is bouncing off of the pulley. The pulley has an alternating Sharpie mark and no Sharpie mark, and that's what it's reading off of. The Hobbywing is in the test chamber. This is the sunroom because I make very poor choices. Let's just start somewhere. Safety glasses. Kind of hard to put on with this head cam, but you know, whatever. We're at 50 volts. The voltage is being measured at the capacitors. This is current here. RPM. 7,700 RPM, just a low power. Get to know you kind of run. Let's go up a good bit. 17,000 RPM, 72 amps, and 47 volts. The pulley ratio is 14 teeth on the motor pulley and 18 teeth on the impeller pulley, giving us a ratio of 0.77 repeating. We saw 17,783 RPM on this funky vintage calculator, and then obviously we'll multiply that by 0.78. That's 13,800 impeller RPM. Just to note, the MGM LMT combination was only able to hit about, I think around 27,000 impeller RPM. And that was a much, much, much more capable setup. So running the compressor into choke really does make a big difference. And what I'm not digging about this setup, in all honesty, is the belt temperature. It's just under 100 degrees, but it's like 60 degrees in here. The belt temperature does get rather hot, and that may be a weak link. All right, let's up it a little more. Starting to get a little scared, actually. It's 162 amps and 24, what was it, 23,500 RPM. That was about 18,000 impeller RPM. It was almost 200 amps. Well, might as well go all the way. All right, this is all this combination has to offer in terms of current draw and torque. We were almost all the way before. 231 amps. I didn't get to see all that. That was kind of scary. I'm right next to this freaking thing. I thought this was a good idea. I must be an idiot. Well, let's see what kind of current draw we see. Let's focus on the meters right now. 28,230 and 40. So our voltage drop got down to 40 and 28,000 motor RPM. Wow, that's pretty good. And times 0.78. That's 22,000 impeller RPM. That's actually better than I expected this setup to do. I was drawing 200 and some odd amps. That's pretty clear. Let me check the pulley temperature. She seems to be holding. I think I'm going to end up having to change the pulley ratio. There we go. Wow. So we hit a high of 132. In that short test, that thing shot up to 132 degrees Fahrenheit. That may end up being a weak link, is that belt drive. I'm going to run it one more time. I know it's hot. I want to see the current. That's enough. And it's going to get scarier because I'm about to put the restrictor in. Note to Vesk. This is how it should work. You just hook it up and it works. And a quick note about the controller while we're here, by the way. This is the most basic controller. This is the first one I use. It's basically two servo testers and a relay. When I hit this button, the relay switches from one servo tester to the other. In this case, it goes from 0% throttle to 100% throttle. The relay is fast enough where it doesn't screw up the ESC, surprisingly. This is arguably the most primitive controller, but it's probably the most reliable, actually, because it's not very subject to EMF interference. All right, let's put the Snorkus in place and see what she does. Okay, restrictor's in, which means we should see less current draw, but more RPM. Let me just reset this meter and reset this meter. They like to go to sleep. After all that testing, we're at 49.3 volts. I'm already seeing some weaknesses of this setup, but I'm also seeing very promising results. Let's back off our... Well, we're going to do this in 2 steps. The pulley's a little bit warm right now, but it's not hot. It's got to be in the 90s maybe. Let's hit it. Did you notice how much further the current dropped? That was like no draw. Why? Because it's restricted. Screw it, we're just going for max. Let me just check the pulley temperature again. I think I saw about 120. I'm going to give it about a minute to cool down. All right, this is supposed to be a torture test, so let's not give it any more time. Just reset the meters. This is full power. I already know what the weak link is, but we'll review it when we look at the data. Let's hit it. Okay. I am right next to this thing. That was stupid. That was intensely stupid. I think we saw about 35,000 RPM, which gives us impeller speed of about 27,000 RPM, which honestly, we know we would hit on the car. We wouldn't quite hit that, but the current draw was almost nothing. This may be the most efficient setup we've built so far. And I think there's a lot more to be had. The Hobbywing's not even warm. I've been touching it. It's quite cool, but the fan runs on it the whole time. That's freaking dangerous is what it is. I'm like a safety moron. I'm doing something incredibly stupid as safely as possible, but it's still incredibly stupid. The pulley's a little too hot to touch. The motor's warm. The Hobbywing is cold. I'm going to kind of go over here real quick. Hi. Just out of curiosity, 45 times 131. It's only 6 kilowatts. Whereas before we saw, what, like 230 times 40? That's barely, not even 10 kilowatts. You heard me continuously harping about how the belt was the weak link in that setup. I don't actually think the belt is the weak link in that setup. The weakest link is the batteries. We projected about a 6-volt drop. We got closer to a 9-10-volt drop. So I think we're going to, and we saw the same thing with the LMT-MGM combo too. So I think we're going to introduce something known as the Alex constant. The Alex constant is calculate your voltage drop, add a little bit of fudge to it, multiply by 2, and you won't be disappointed. Now, that's not to say that the second weakest link isn't the belt drive, and the pulley ratio needs to be adjusted. I think I'm going to switch to 16-tooth motor pulley. I think that's closer to optimal. That'll put us where we need. And also, we need some stronger batteries. Now, I have 36 more of those massive LTO cells where 24S1P, so no cells in parallel, just a single string of cells, was able to push almost 700 amps in the LMT MGM combo with not too much voltage drop. So a single set of 20 of those cells in series will give us, they won't even be breaking a sweat driving this. So that'll give us more RPM, you know, because brushless motors are completely voltage dependent. Of course, it's going to increase the current draw. We basically have to get to like 46 volts at 280 amps continuous to get to where I want to be. The Hobbywing ESC has no problems getting us there. And why do I want to be there? Because I have 2 P2 units now. Oh, by the way, the sensor cable did come in, and I tested it, and yeah, it does make a difference, and yes, it does work. So there you go. Thanks so much for watching. If it wasn't for you all watching, I certainly wouldn't be doing this. This is kind of nuts, but it's fun nuts. Let's have fun with nuts stuff. So thank you all for watching, especially thanks to my patrons, because without them, you know, this would definitely not be possible. And, you know, give me a thumbs up. That certainly also even helps the channel quite a bit. And, you know, there's more stuff coming up. So I'll catch you all in the next one. Thanks.